video, we are going to talk about periodic trends. Now, you're all familiar with the periodic table and how it's organized. And you may already be familiar or aware of the idea that the elements are grouped by property. Not only are they organized in terms of increasing atomic number, but also by the types. So metals are with nonmetals, metals are with metals, nonmetals with nonmetals, but also that the way they're grouped reflects similar properties. So for example, the group 1 metals like lithium, sodium, potassium, and so on, they all do very similar chemical reactions. They have some similar properties. They're all kind of shiny, soft metals. The noble gases are also all similar. They are all non-reactive gases. The halogens also, so fluorine, chlorine, bromine, iodine, all do similar types of chemical reactions. Now, there are other bits of information wrapped up in the periodic table that we can use to get a sense of what an element, what properties an element might have, or an atom or an ion, in fact, might have, just by its position on the periodic table. And it's very important that while we look at this, we remember that the periodic table is a human creation, and the table itself is never an explanation. And you'll see what I mean as we go forward. But the important part of this to remember is that all of the trends that we are going to look at, the roots of those trends are actually in atomic structure. So how big is the nucleus? How many electrons are there? How are those electrons organized? Those structural features are reflected in the periodic table. So we're going to look at things like trends in atomic radius, so how big an atom is, or trends in how much energy it requires to remove an electron from an atom. So that would be ionization energy. Now, what is important to me as your instructor is that you understand that the explanation for something is never the position on the table. Okay? So I'll give you an example, a very simple one. Sodium, the sodium atom is bigger than the lithium atom. We're going to talk about, I'll give you a refresher on why that is afterwards. But it's never the correct answer to say, well, sodium is lower down on the periodic table than lithium, so it's bigger. That's not the right answer. You need to be able to explain the difference based on the structure of an atom. You can use the periodic table to guide you into figuring out the answer, but that's not the explanation. And we'll talk about what the explanations are in a minute. So the first thing I want to talk about is atomic radius, or how big an atom is. The first thing we need to do is talk about how do we measure the size of an atom. If we look at atoms, we know they're spherical. Measuring the size of them is not a trivial thing. Now, there are some modern microscopy techniques that let us look and attempt to measure the size of atoms. So these were things like atomic force microscopy, scanning, tunneling microscopy, and other really cool techniques. The classic method for determining how big atoms are is using X-ray crystallography. So X-ray crystallography works a little bit like the diffraction experiments that we saw when we were trying to understand the wave nature of matter. Basically, nuclei act as if they are little slits that you can shine X-rays through, and the X-rays diffract. And based on the diffraction patterns, you can figure out how far apart the nuclei are from each other. Now, if I have an atomic solid like a crystal of krypton, right? So you freeze it down until it's krypton ice, basically. And I find out that the distance between, I can measure the distance between two nuclei here. Well, logically, half of that distance is going to be the radius of a krypton atom. Now, I can do the same thing for covalent compounds. If I do it for bromine, for example, with molecular bromine, I can find out that the distance between the two nuclei of a bromine molecule is 228 picometers. And so half of that is 114 picometers. Now, it's important to realize that because of how covalent bonds form, if I use a covalent compound, the measured radius will be a little bit smaller because of orbital overlap. And we're going to talk a little bit later about how covalent bonds form. The next thing, so the first thing I want to look at is what is the trend in atomic radius? And it's a bit counterintuitive. So if we look across this, what we see is overall atoms get bigger as atomic number goes up, but it's not a straight line. So let's take the case of starting way over here. This would be hydrogen, the first element. And hydrogen is actually a little bit bigger than helium. And we're going to talk about why that is in a minute. But now if we move to helium, from helium to lithium, we see lithium is bigger. Now this should make sense to us because both hydrogen and helium have their valence electrons in 1s. But once that's full, lithium puts its valence electrons in 2s, and 2s is bigger than 1s, so the helium atom should be bigger than either of those. What's interesting to see is that as we go across that row, so lithium, beryllium, boron, and so on, the general trend actually is that the atoms get smaller as we go across the periodic table. And this trend is generally repeated. And it gets a little wonky, but what we're mostly interested in here is that general trend. So if we look at, say, this, so again, as we go down a group in the periodic table, so for example, if we take the noble gases, helium, neon, argon, and so on, as we go down, those atoms get bigger. And again, it should make sense. Helium's valence is 1s. Neon is 2p. Argon is 3p. Krypton 4p. Xenon 5p. So they are big. The electrons are in larger orbitals. But as we go across the periodic table, the general trend, and there are exceptions, we're not really going to pay too much attention to those exceptions. As we go across the periodic table, the trend is that atoms get smaller. Now, the first thing to realize is that this, in and of itself, shouldn't be too surprising, because we already know that, for example, 2s orbitals are larger than 2p orbitals. So if I am looking at, say, the difference between lithium or beryllium and boron, let's take a look at that. So beryllium has 1s2, 2s2. And then if I move to boron, boron is 1s2, 2s2, 2p1. Now, sure, there's more electrons, but 2p is smaller than 2s. So those electrons are actually not being added outside to some orbital further from the nucleus. Yes, the 2p orbital is higher in energy than the 2s. And if you remember, that's because the 2s orbital penetrates close to the nucleus. But that doesn't necessarily explain why it gets smaller. So we're going to talk about that now. So this comes down to a phenomenon known as shielding and effective nuclear charge. Let's take the example here of lithium, of the atom lithium. Now, lithium has a charge of 3 plus, and it has 3 electrons. Lithium, it has 1s2, 2s1. These are core electrons, and the 2s1 is a valence electron. Now, what I want you to imagine is that the core electrons, because they're closer to the nucleus actually absorb, if you will, a full +1 from the nucleus. What does that mean? Well, it means that the outer electron is shielded from the full force of the nucleus. The outer electron, the valence electron, doesn't feel the full attraction of the nucleus. It only feels what we would call the effective nuclear charge. In this case, +1. So it's as if that one electron is being held onto by just +1. Now, that's the basis of this. But what about when we get to something else? Why, for example, is beryllium then smaller than lithium? All right, so this is my very poor mock-up of beryllium. Now, beryllium has an electron configuration of 1s2, 2s2. So again, it has 2 core electrons, but now it has 2 valence electrons. So if we think about how this works, the valence electrons, now the nucleus has a charge of 4+. We can just ignore this for now. The nucleus has a charge of 4+. The core electrons, they're still just 2 core electrons. So those electrons are going to shield those core electrons by +1 each. So we're going to subtract 2. So that leaves a charge of +2. But what about the effect of the valence electrons on each other? And this is where it gets tricky. The valence electrons shield each other, but only a little bit. They occupy kind of the same space in their wave function, so they shield each other a little bit, but not a whole amount. This, for example, electron does not shield this electron by a full +1. It's a fraction, and there are some arguments about how much that is. Is it a half? Is it some other number? And the truth of the matter is it's not that important, but I will show you. The way we work this out is something called Slater's rules. So Slater's rules say that the effective nuclear charge, so the charge felt by a valence electron, is equal to the number, is equal to the atomic number, Z, how many protons, minus this S factor. And the S factor is basically the number of core electrons, right? Because those shield completely, and some other amount, so the number of valence electrons minus 1 times some fraction. And there's a still dispute, and it doesn't really matter. The original Slater's rules have this number at 0.35. Now, I'm not going to ask you to do any math with this, but the math is useful for illustrating the situation. So if we look at the case of beryllium, so effective nuclear charge for beryllium is equal to Z minus S. So now remember, when we talk about effective nuclear charge, we're talking about how much attraction is one valence electron experiencing. So it has 4 protons minus 2 electrons, 2 core electrons, plus 0.35 times 1, because it's 2 valence electrons minus 1. So that's 4 minus 2.35, which is equal to 1.65. Now, some people just make their life simpler and use the number of valence, the factor that they multiply by as 0.5. It's fine. It doesn't really matter. But what does this tell us? It says that the valence electrons in beryllium, so if we take, so it tells us that in lithium, the effective nuclear charge is equal to 1. That's not a very nice one. The effective nuclear charge is equal to 1. In beryllium, the effective nuclear charge is equal to 1.65. Now, we know that the energy of attraction is proportional to the product of the charges over the square of the distance. Now, if the charges increase, so the attraction is greater, the radius will decrease. So a greater attraction means a smaller radius. So when we are looking at what happens across the periodic table, so when we were trying to understand what's happening across the periodic table, what we see is that the effective nuclear charge increases as we add protons, even though we're adding more electrons too. But because we're adding electrons to the same orbitals, to other valence orbitals, then the effective nuclear charge increases and the atomic radius decreases. Now, shielding and effective nuclear charge are not the explanation for why atomic radius increases as we go down the periodic table. And as we go down the periodic table, it's very simple. Valence electrons are in orbitals with a higher value of n. But as we go across a row, the general trend is that effective nuclear charge increases, and so atomic radius decreases. Now, what about ions? Now, it's a little trickier to understand what's happening with ions, and I regret that these numbers are a little bit small, but the thing to realize, we're not going to necessarily categorize these relative to each other, but rather I want you to understand, how do these behave? How do we compare the size of an ion relative to its parent atom? So if we think about cations, right? So if we compare, say, lithium and lithium plus is significantly smaller than lithium atoms. And this is always true. Cations are always smaller than their parent atoms. All right. And if you think about why this is, well, what happens when we go from lithium to lithium plus? We are removing the valence electrons. We're left only with the core electrons. And those core electrons feel the full pull of whatever nucleus there is. So they are going to be very small. All right. And so this is the general trend. Cations are always smaller than their parent ions. And the reverse is true for anions. Now, so anions are always larger, and dramatically so. Now, this one's a little bit trickier because, as you know, when we're making anions, we are not moving up to a higher energy level. So it should be relatively straightforward for you to understand that, right? If I have lithium 1s2, 2s1 versus lithium plus, which is just 1s2, right? Smaller, because the valence is in a smaller orbital. But what about chlorine and chloride, for example? So if I have chlorine, right, I have 1s2, 2s2, 2p5. And that has a radius of 99 picometers. Cl minus has 1s2, 2s2, 2p6. And that has a radius of almost double, 183 picometers. Now, I haven't moved to a larger orbital. I haven't put electrons in 3s, for example. All I've done is added one more electron to the 2p orbital. But what happens is this additional electron brings repulsion. And what happens is the p orbitals actually stretch out, they elongate to try and reduce the repulsion in the atom, or in the ion in this case. And so they get bigger because now the nucleus isn't big enough to compensate and hold them together as well. ionization energy. So ionization energy refers to, now, ionization energy is very specific, okay? So yes, we can form an ion by either gaining or removing, adding or removing electrons to an atom, right? However, the term ionization energy refers to one of these things very, very specifically. And it refers to how much energy is required to remove an electron from an atom or from a particle, or from another ion, right? So ionization energy refers specifically to the amount of energy required to remove an electron, right? So it would look something like this reaction. Lithium, for example, the equation that we would write for the ionization of lithium is lithium, and they're always in the numbers we have are always in the gas phase. So it would be like lithium goes to lithium plus plus 1 electron, right? That is a oxidation, right? If you remember back to NYB, right? Yeah. Lose electron. Yeah, it's an oxidation. And the delta H is, in this case, it happens to be 520 kilojoules per mole. There's a few things that you need to know about ionization energy. So we're going to talk about ionization energy. The thing to note about ionization energy is always endothermic. It always requires energy to remove an electron from an atom, all right? And if you think about it, that makes sense because you have a positive nucleus and a negatively charged electron, and opposite charges attract. So you want to always, it requires energy to remove an electron away from a nucleus. Now, there are trends that show up in the periodic table. And again, it's really important to realize that the periodic table lets us see the trend, but it's not the cause of the trend. All right. So we're going to ignore hydrogen again because it's, well, it fits. But the general trend in the periodic table is that as we go down a row, the first ionization decreases. All right. And then, so if we look from lithium to sodium and so on through these guys here, what happens, even starting with hydrogen, it gets easier and easier, right? Remember, it's less and less endothermic. And when something is less endothermic, it requires less energy to do. So as we go through these guys here, it becomes easier and easier to remove that electron from these guys. All right.
Okay, ready?
Yeah, you can see it.
Good?
He's so disappointing.
Oh.
So
He ran away. I think it would be cool in the dark.
All right, we ready?
Yes.
All right, I'm gonna put the thing down. This one's not as quick at the start, and it might just not do anything. It could literally go anywhere.
Give me something to work with, right?
Look, it's going to circles.
Is it sparking at all?
Yeah. Oh, there we go. Oh, some fire explosion I wanted.
That's the best, 'cause it's gonna spark and do that for a long time, hopefully.
Wow.
Fascinating.
Oh, and remember, anything you say will be on my YouTube channel later.
Wow.
Hi guys.
Subscribe.
Follow me on Instagram.
Hit that like button.
It's like a circle. It's taking forever. It is taking forever.
You now know how spoiled you are. You're like, that explosion thing wasn't cool enough. All right, here we go.
It's so dramatic. Oh, finally.
That's pretty dope.
If the beer is hot enough, will it break?
So you can't really take this as a qualitative or quantitative measure of reactivity because he's not controlling for the size of the metal chunks. But you can see even though this is really like sparking and flashing, in fact, it doesn't react as consistently as the sodium, as the potassium. The potassium caught fire.
Get it.
All right, let me see if I can get some.
I don't know,
So
I don't
you
know.
see this splatter here?
Spray it.
So if I spray it, it might fizzle once it kind of dissolves a little bit.
All right.
And you can see the lithium here is reacting very, very, very slowly. So it's less dramatic. It would have been better if they did this, honestly, in the opposite order, because it would have been more dramatic to see, sort of bigger and bigger reactions over time. So this is a bit backwards. But what we definitely see, if we just look at these ones, lithium, sodium, and potassium, that as we go, what on earth is as we go down the periodic table, they get more and more reactive. And that's because less energy is required to remove the electron, so more energy is available as the reaction proceeds. Now, I don't know if any of you ever saw this one, the Brainiac alkali metals in high school, if your teacher ever showed that one to you. It's fun to watch, but it's fake. It's not like they faked the explosions for it. There's just like, if you do the math for like your gas law calculations and thermodynamic there's no way the explosions they show. It's fun to watch because it looks really awesome, but it's not true. So there you go. So the idea here is, as we go down, remember, so as we go down a group, right, what happens is it gets easier and easier to remove an electron. And as we go, so if we think about this one just in and of itself, okay, so there is a parallel here between this and the size of an atom. And if we stop to dig a little deeper, we'll realize that in fact these things correlate perfectly. So remember, and I mentioned this a while ago, but this equation, the Coulomb's law, dictates a lot of stuff about the properties of atoms. And so if you think about it, right, we said the force of attraction between the valence electrons and the nucleus is dictated by this. So the charge of the nucleus, or in some cases the effective nuclear charge, and the distance between them. Now, as we go from lithium to sodium, potassium, and so on, what changes? In hydrogen, right, the valence electron is in, n equals 1, right? In lithium, it's in, n equals 2. In sodium, the valence electrons are in, n equals 3. So as we proceed, what's going on? The electrons, the valence electrons, are getting further and further away from the nucleus. So what's happening is as they get further and further away from the nucleus, the electrons are held onto less tightly. Right? So it becomes easier to remove them simply because they're further away. So that's the main factor here, is that as we go down a group, right, the valence electrons are further and further away, so they're held onto less tightly. That's the effect within a group or a column. But if we look at a period, as we go across the periodic table, we see a slightly different effect. But again, it parallels, and so it parallels what we saw with atomic radius, right? As we go across the periodic table, the general trend is what? Is that it actually gets harder and harder to remove an electron. So what do we see? As we go across a period in the periodic table, what do we see? We see that what do we know? We know that across the period, yeah, the effective nuclear charge increases as we go across the period. And then radius gets smaller because the effective nuclear charge goes up. Across the period, we know that the atoms get smaller, and the reason is that Z effective, the effective nuclear charge, goes up, all right, because of the way shielding works. But so again, because the size of the atom is dictated by how tightly those valence electrons are held onto by the nucleus, well, that's the same force that is dictating how difficult it is to remove an electron. If if the effective nuclear charge goes up, it becomes harder to remove an electron. That's all. And so we see that the first ionization, and remember, this is a trend just in first ionization energy, right? As we go across, the general trend in first ionization energy is that as we go across the periodic table, it gets harder. Now, it's not fully the case. There is some stuff where it's we see it gets more endothermic, but then it actually gets a little bit it does jump around a little bit. Like one of the cases that's a little bit complicated is here, where we go now. You see there's always this kind of jump between, let's say we go from beryllium to boron, right? So if we look at beryllium has a full s orbital, and then boron, we're starting to look at removing an electron in a p orbital, right? And so the differences that come there are a little bit tricky to quantify, and I don't want to spend too much time on it. But if we compare these ones, like it's significantly easier to remove an electron from boron than it is from beryllium. Now, this has to do with how s orbitals versus p orbitals penetrate to the nucleus. So remember, we talked about when we were talking about Aufbau and the filling of orbitals, we said s orbitals penetrate closer to the nucleus. And when we get here, what happens is because the s orbitals penetrate close to the nucleus, that outweighs kind of the effective nuclear charge. This is a tricky one to explain, though. One that's a little bit more obvious and maybe not as dramatic. And so it is, say, the difference between nitrogen and oxygen. So you notice that the first ionization energy of nitrogen is about 1400, and the first ionization of oxygen is actually this. Now, this is a little counterintuitive. Remember, what we're talking about here is the energy required to remove an electron, right? And normally we don't see things like N plus or O plus. But the difference here, if we look at nitrogen, so nitrogen is 1s2, 2s2, 2p3 like this, and oxygen looks like this. So in the case of nitrogen, right, the electron we're removing, this would be the electron removed in first ionization. But in the case of oxygen, it's this one. And the difference here is that we are seeing the removal of a paired electron versus an unpaired electron. So even though it should, in principle, be harder to remove that first electron in oxygen, what we're actually seeing is that it's a little bit easier because it's paired versus unpaired. Now, these trends in ionization energy are also at the root of why, For example, metals form cations, right? Metals lose electrons, and nonmetals gain electrons. Because if you look at this, there's a big difference here in how much energy is required to remove an electron from lithium versus fluorine. And so it's not that you can't remove electrons from fluorine, you can, but all of this is relative to the energy situation on Earth, right? We are not inside a star, for example, right? We are not inside a supernova. So we don't typically see very high energy species relative to our environment. So what do we see? We don't see F plus existing in nature, right? Not that it can't exist in nature, but it requires a lot of energy to form, and it probably requires a lot of energy to continue existing. Whereas something like lithium plus is a lower energy species, and so it can exist on Earth comfortably. All right, so the general trend in ionization number, again, follows the same overall pattern as the one we see in atomic radius, which is as we go down a group, so if we follow, say, from helium to neon, argon, and so on, what happens is the atom gets bigger, and so the valence electrons are further away from the nucleus, and so they are easier to remove. In contrast, across a row, so say from lithium to neon or sodium to argon, effective nuclear charge increases, and so it becomes more difficult to remove an electron. And the transition metals are messy, so we're not going to worry about those. These are the overall trends in the periodic table. This is what we just talked about. Now, obviously, we're not limited to one ionization. In some cases we are, but not always. Now, the trend that we see really just follows first ionization. That's the trend. But there are some other interesting things that happen with subsequent ionizations. So if we take the case of sodium and magnesium, which are adjacent to each other on the periodic table. When we look at these ones, what we see is, so sodium and magnesium, it follows the basic pattern where the first ionization of sodium is easier than the first ionization. But we see the way in which the ionization energies increase is not really equivalent. Now, when we talk about ionizations, in terms of energy calculations, we always treat ionizations successively. So for example, we know that magnesium, actually magnesium gas, right, would be go to Mg2 plus 2 electrons, right? So if we were thinking about this in terms of a redox reaction or something like this. However, when we're doing energy calculations, we have to treat them one at a time, right? So this, we can't really use this. What we would have to say is we have, all right, magnesium gas goes to magnesium plus an electron, and then magnesium plus goes to magnesium 2 plus an additional electron, all right? This would be the first ionization energy, i.e. E1. This would be the second ionization energy, i.e. 2. Now, if we think about it in terms of just electrostatics, so Coulomb's law, it makes sense that the second ionization energy is more difficult or more endothermic than the first ionization energy, all right? Because the effective nuclear charge of the remaining valence electron, the effective nuclear charge felt by the remaining valence electron is significantly higher. But what we notice, so it gets harder. What we notice with sodium, if we had sodium gas going to Na plus an electron, that would be ionization energy 1, right? And that's here, right? And the second ionization energy of sodium is here. Now, the difference here is in both cases, it got harder to remove an electron, but in one case, it got a little bit harder, right? It's roughly double. In the other case, it's like dramatically harder. It's like almost 10 times more difficult. In terms of the electronic structures of sodium and magnesium, is there a reason or an explanation for why it's so much more difficult to remove the second electron in sodium versus the second electron in magnesium, sorry. If we think about the electronic structures of sodium versus magnesium, so if we have sodium, right, it's 1s, 2s, 2p, 3s. Right, so this is sodium. If I remove this electron to this, so right, right, which means that sodium plus is going to look like this. So it only has core electrons left. All right, so the next electron removed would be, right, this would be, right, and it's a core electron. So, and removing core electrons is very, very difficult because they are held onto very tightly. Remember, core electrons essentially feel the full attraction of the nucleus. Whereas in the case of magnesium, I'm not going to write the whole thing out again, but magnesium has 2 valence electrons. So that means that when we're removing the second one, we're still removing a valence electron. Then we see the big jump for the core electrons. And this is a pattern that we see in ionization energies all the time. Right? Basically, every time we remove all of the valence electrons and then we want to start removing core electrons, we see this huge jump. So we see it after the first one for sodium, after the second one, right? The third ionization of magnesium. Aluminum, right? Aluminum has 3 valence electrons. So what do we see? 1, 2, 3, relatively easy, and then a giant jump to try and remove the 4th electron. Same thing, the trend continues. All right, now the opposite of ionization energy is electron affinity. So electron affinity is the energy, and this is a terrible table, actually. I should point that out. I should stop using it at some point. But so electron affinity is the energy involved in adding electrons to an atom, so making anions. So now, here's the thing. The signs on this table are all messed up. All of these numbers should be, the numbers should be negative. Because the first electron affinity is almost always exothermic, except in these cases, right? These ones should actually all be greater thans. This is the worst table. And then I guess that makes me the worst for continuing to use it, right? So first, EA is generally okay. So, and there isn't really a great trend. So I'm not really going to ask you about trends in this. But what we do overall see is that it's more exothermic for nonmetals to accept electrons. Basically, it's more energy favorable for nonmetals to accept electrons. Right, so we see that, basically as we go from, if we look just at the P block, then we see that it gets easier, or it gets more exothermic. The catch is that the second, so subsequent electron affinities, and third, etc., which typically we don't see, are endothermic. So even though adding the first electron is an endothermic process, adding subsequent electrons, the first electron is exothermic, but then subsequent electrons are endothermic. The last trends, are these the last one? The last trend I actually want to discuss is the trend in metallic character. They are shiny, they conduct heat and electricity, they are malleable. The other one is that they can be drawn into wires. They're ductile is the word, right? So the way we make copper wires for electrical appliances or whatever is they take copper and it gets stretched. They take a piece of copper and it gets stretched into wire. So we have shininess or luster, conductivity, heat and electricity, and malleability and ductility. So it can be drawn into wires. All right. And so those are the physical characteristics of metals. And we tend to, and so basically what we see is we tend in our everyday life not to associate the groups 1 and 2 elements with metals, but in fact, they are the real metals, the true metals, if you will. They are the most metallic of the elements. And in general, metallic character increases as we go down the periodic table and decreases as we go across it. And so we tend not to think of, say, sodium or lithium or magnesium, although magnesium is one that we come across more often, but say sodium and lithium and potassium as metals because they're so reactive, as we just saw in our video, that we don't, on Earth in nature, they don't exist in their metallic form. They are always in a mineral, they've reacted with something. And we, for example, sodium, I don't know if you've ever seen sodium. It's a shiny metal, but you can cut it with a spoon. It's super soft. All right, and the same is true for lithium and potassium. The things that we typically consider as metals are transition metals, so the elements here, right? And that's because they are less reactive. They're also more abundant and easier to convert into their metallic forms, right? So iron and copper, nickel, zinc are the ones that we typically consider to be metals because we encounter them as metals in our everyday life. So as a general rule, what happens is as we go down a row, down a column, elements get more metallic, and then as we go across, they get less metallic.